More properties of operators coming up. Here we're dealing with an anti-Hermitian or Skew-Hermitian operator, which is equal to the minus of its Hermitian conjugate. So we just have a minus sign there instead of having just the q hat dagger equal q hat, which was the Hermitian definition. And with this, we want to show over 5 parts some of the properties associated with anti-Hermitian operators. So we want to show that the expectation value of an anti-Hermitian operator is imaginary. That'll be useful later. B, we want to show that the eigenvalues of an anti-Hermitian operator are also imaginary. C, show that the eigenvectors of an anti-Hermitian operator belonging to distinct eigenvalues are orthogonal. That'll be fun. Part D then, show that the commutator of two Hermitian operators is also anti-Hermitian. How about the commutator of two anti-Hermitian operators? And then finally in part E, show that any operator Q can be written as the sum of Hermitian operators A and anti-Hermitian operator B, and give the expressions for A and B in terms of Q hat and its adjoint Q dagger. This is kind of reminiscent of things we did in chapter 2 with the linear combinations of even and odds. So we'll kind of use that method there. But pretty fun question. Let's dive in. All right, so for beginners, we want to know, well, if we're trying to prove that something's imaginary, what does it mean to be real or imaginary? In which case, we know that by the conjugate definition, we're real if the conjugate is equal to itself. And here we're imaginary if the conjugate is equal to the negative. Here I'm just using this I to represent that we're the imaginary part of the complex number, not the real part. So just be aware. There's not a real good notation there, and I'll clarify this as well. But nonetheless, let's go ahead and dive in. For A, we have a pretty easy setup here. We just have the expectation value, which by definition means that I have it acting on a wave function to the right, and then I have, of course, the inner product with the wave function. This was the psi star operator psi that we had in chapter 2 and chapter 1 when defining things. But I know that I could have within these operators, I know that if I want to bounce this over, I can do so at the cost of the transpose conjugate or the dagger. Okay, so in doing so, since I'm dealing with anti-Hermitian operators, I can't just leave it as Q, I have to put a minus sign there. And that's what we show there. So that's where we get the minus sign and put it there. And so, we know that linearity, we can bump that negative sign out, no big deal. Here in this line of thought, we could also switch back the order using the switching property of the complex, or rather of the inner products, with the complex conjugate. Noticing here that I could switch the two, no big deal, and I'm left with the just at the cost of the complex conjugate, the star up there. And so here I'm back to the same quality definition of the inner product for the expectation value, so I can verify that this is equal to the negative and the conjugate. So I'm pretty good there, but what about drawing our conclusion? Well, the complex conjugate here tells us that if I push this negative over, I have the negative on this side, and that's equal to the complex conjugate, so I verify that I am just an imaginary thing. Again, I just want to point out that this I am talking strictly about the imaginary part only, not the whole form of complex numbers. There's just not a good notation for it, so my apologies there. Um, and so if we move on to the eigenequation for part B, we see that the operator acting on a wave function yields some scaling quantity known as the eigenvalue, also scaling the wave function. So, if we talk about linear algebra, eigenvectors, all that stuff, this is where it's coming from. But here, let's go ahead and make sure that we're in the inner product definition. So we take the inner product, here's just the wave functions, this is the operator, so it has to operate on something. And so we see that if we have to do it to the left-hand side, we do it to the right-hand side. No big deal. We see that this collapses down into this and forms a new vector here. So this is just a matter of notation and definitions. That's cool. what I'd like to point out here is that now that we see that this lambda is just chilling with the psi here, we know that we could use the definition from linearity to bring it out front. So, of course, our linearity keeps coming back. If we use this, we could factor it out. So that's the Q right here coming outside, like we factor there. No big deal. We've seen it before. We could pull out scalars. Totally fine. But then we also know that if I stick with this thing and I bounce this operator over to the left-hand side, again, I am color coding these just so that we know that we can see where the operator is bouncing to and at the cost of what. But these are the same function, so the inner product should go to 1. No big deal there. And so with this, what we know is that if I bounce this over, I have to, at the cost of a minus sign, which is what we saw here, bounce this over, cost of a minus sign for anti-Hermitian. And of course, I know that since I'm acting on the purple function, I get a scaling factor of lambda again. But since I want to left-hand factor out, I do so at the cost of a negative. And so, or rather a complex conjugate, just due to how the inner product was defined. No big deal there. But again, we see that we conclude to the same result about, lambda, if it's equal to the negative, then if the complex conjugate is equal to the negative, again, we showcase that we are imaginary only, and we're pretty good. So not too bad there. Those two are pretty quick and easy. The next couple are going to take a little more processing power and very careful with the definitions. So let's go dive into those, but we'll take our time. All right, so here we want to be careful with the fact that we were told a couple things in regards to this particular problem. If Q gives us lambda when it acts on psi, okay, then Q when it acts on phi gives us mu. We were told that these were distinct eigenvalues, and we want to show that if this is the case, we can verify that the eigenvectors are orthogonal. Okay, so here, let's just take the definitions again, apply them across. We see that we get here, if we're applying it to this eigenequation here, we're just, take the inner product with phi, and we see here that we get phi lambda due to the fact that we have Q operating on the green wave function. That gives us lambda in the wave function. No big deal. As you see, linearity comes through again. We love that. We're good, and we're happy with that. Okay, so, but we also know that if we're in this stage here, we can bounce this over just like we did to the last two properties. And if we bounce this over, we do so at the cost of a minus sign. Thank you, linearity, for bringing it outside. And now we see that Q is operating on phi. And so if that's the case, that we have pretty nice results here. And we could, use the fact that this is equal to mu and bring it outside with the conjugate. No big deal. But we also saw that in part B, we already knew these were imaginary, so the negative with the conjugate just equaled the same thing itself. That's pretty cool. I like how we get to use the same result or something that we just proved here. So we like that. Pretty nice. Now here, what we want to do is pretty unique. Since we have this expression on the left-hand side and this expression, if we take the difference, we can get rid of the left-hand side of the argument, and it puts all the focus on the right-hand side. And so by doing so, we see that by getting rid of the left-hand side to a 0, and you see that both of these terms have the phi and psi wave function in a product, we know that we have lambda minus mu. Now, in order for this thing to equal 0, that means we have two cases. Either lambda minus mu equals 0, which implies that lambda equals mu, or the inner product equals 0. Okay, now let's be careful here. We were told originally that these eigenvalues were distinct. And if they're distinct, this cannot hold. This is not true. This cannot be the case. So the eigenvalues are distinct, thus lambda cannot equal mu, and that makes us conclude that the inner product equals 0. And of course, if we see that the inner product equals 0, think of things like the dot product. This means that there's no projection of one onto the other, therefore they're orthogonal. That is one of the definitions that we've come to in multiple classes, but that's a pretty fun project to see come to fruition there. And by the way, if you haven't taken linear algebra, this kind of proof and direct proofing it's going to come up again and again, so it's just worth getting used to seeing this kind of layout the way it is. Especially in our next part, the next part of this is going to be definition heavy and substitution heavy. So let's go ahead and dive in. So moving into part B or part D, we have a lot to deal with in terms of the commutators. So let's recall real quick that our commutator definition, regardless of what the dagger is telling us to do, tells us that we want PQ minus QP. That's just the definition. Now from here, of course, we could use linearity and bring this dagger to each part of this, no problem. Here's where we need to be careful. What is this the product of PQ dagger and the product of QP dagger? Well, we actually proved this in an earlier question, namely 3.5 part D, where the dagger of the product is the inverse order, because we have to transpose these operators. Again, we're not assuming they're scalar. So we have to transpose them and see what their their dimensionalities will leak up, i.e. to switch the order, and that's what we do here. Since these are Hermitian though, what we see is that, we can just go ahead and we know that the dagger is equal to the operator itself, so we just clean up here, and then we go back to the definition of the commutator, which is what we see here. Clean that up, we see QP is what's going on. However, how do we compare this to what we were given with the dagger on the original commutator? Well, of course, we could switch the order at the cost of a negative sign thanks to anti-symmetry. No big deal there. We like that. Check. We're cool there. So we see that the commutator of two Hermitian operators is anti-Hermitian. That's pretty weird, but makes sense for commutator algebras. And so now for the second part, what about anti-Hermitian? Well, we kind of have to rinse and repeat. Okay, so here you break it out the same, no big deal. We use the same property from 3.5b, and now we're stuck with trying to evaluate what the Q dagger, P dagger, all those are, which of course we know in the given question that if we're anti-Hermitian, we know that the dagger is equal to the negative of the operator. So you see we get negative, negative, they cancel, negative, negative, they cancel. Wonderful. And then of course we end up in the same position that we did with the Hermitian kind, the commutator, switch it at the cost of a negative sign. So in either case, they're anti-Hermitian. And so that is wonderful, and knowing this, knowing that the commutator of two Hermitian or anti-Hermitian operators is anti-Hermitian, coupled with what we saw in part A with the expectation value of anti-Hermitian operators being imaginary, this gives us the insight that we used to prove the uncertainty principle early. And when we were wondering about why did we have an I multiplying in the uncertainty relationship, that's because we know that the expectation value of an anti-Hermitian operator is imaginary. So the I would cancel with whatever I result comes from this. So that's pretty darn clever, can't lie. Now, that's why we see we're trying to couple all these things together and get our hands, get used to dealing with these definitions and what their ramifications are. Big uses in other places thanks to linear algebra, but enough of me rambling. Part E wants us to evaluate. This is just a matter for remembering that we're trying to define a operator in terms of Hermitian anti-Hermitian pairs. So this is just a matter of defining the operators wisely. Okay, so long as we define them wisely, like we did in chapter 2 with even and odd functions, insofar as how they related to linear combinations, we can get what we need to. And here, let's go ahead and broadcast out, let's just follow the script that we did in chapter 2, where we're 1/2 of something plus something else, 1/2 of something minus something else, and see if these things test through. Okay, so here, if we go ahead and say that we're adding these two things together, so A and B, we see that here we just get 1/2, 1/2, so that's a 2 right there. So we're able to define Q in terms of A and B, which are defined as such, and now we just need to verify that the way we set up A and B are Hermitian and anti-Hermitian. So clearly, if I take the dagger here, I end up with a Q dagger here plus a Q dagger here. The double dagger will undo each other, and so I'm left with A. Okay, so notice that even if I were to have a minus on both of these things, they would cancel out. We're fine there. We just need to see here now that if that's the case with B, if we take the dagger and we're just, defining Q to be Hermitian, we switch the sign here, and the sign switch is what we would factor out, and that's what gives us the negative B. So B is anti-Hermitian, A is Hermitian, and we're good to go for everything that's needed. And it's pretty clever, the linear combinations was clever, this is very clever, and clearly because of the fact that we can write these in this way for any operator that's we're tested with, this can let us have insights with the properties that we proved in A, B, and C. So this is all setting the stage for what's to come, and the author is really good at making you do this stuff now for what's to come later. So thank you for watching, and until next time, stay curious, happy learning.